charging cord for a little while anyway. Maybe not too long, but for a little while. All right. We talked about how to make alcohols. You could, hydration of an alkene makes an alcohol. The hydrogenation of an aldehyde or a ketone makes an alcohol. We talked about the reactions of alcohols, particularly oxidation. Primary, secondary, and tertiary alcohols oxidize differently. Not sure we looked at any other reactions, but let's look at this one. The dehydration of alcohols. And before we get deep into this major and minor product considerations, let's just look simply at what we're talking about. Well, over here it says we're going to, a water molecule is eliminated from an alcohol. So we're going to take an H2O molecule off of an alcohol. Or if you want to consider that as an HOH. That's H2O. That's two hydrogens and an oxygen. And in a number of these, as I lay these reactions out, it's just what I'm going to say. All of those lines around there are hydrogens. But I want you to look at these two hydrogens. What's so special about those is that they are sitting on the carbons right next to that hydroxyl group. They are the hydrogens adjacent to the OH. They are the only hydrogens that are accessible to that OH group to remove as a water molecule. All right? So dehydration of an alcohol involves, removing a water molecule. And the kind of the way that proceeds, you know how I am with the dots. We've got that line is 2 electrons. This line is 2 electrons. And what happens, for that water to go away, the hydrogen and the oxygen needs to form a bond. Needs 2 electrons to do that. That leaves 2 electrons behind, which move on up into here, which creates a double bond and water. That's the dehydration. This is what's happening. All right? Bonds, chemical bonds, is the sharing, and particularly with these covalent compounds, come about by the sharing of electrons. So the hydrogen-oxygen bond here only needs 2 electrons to complete that molecule, and that leaves 2 electrons behind to come on up where this single bond already was and form a double bond, an alkene. So the dehydration of an alcohol produces an alkene. All right. All I wanted you to see here is you could either, or what I wanted you to see here, is you could either remove this hydrogen here that I have pictured with that OH and get a double bond there. Or imagine here, I'll just put dotted lines around this. You could have removed that one, and what would you have gotten? You would have gotten this. And what is our alcohol, by the way? What's the alcohol that we're starting with? 2-propanol or isopropyl alcohol. Okay? So we're starting out with that OH right in the middle there. I put it in the middle so that we could have two hydrogens to choose from. But in this particular case, if I got that product or that product, is there any difference between those two products? Those are superimposable on one another. They both have the same name. One, or not even one propene, propene. Simply propene is the name of our product. That's propene, that's propene. And that molecule I could take and superimpose it on that molecule. If I had models of them, I could do the same thing with models. There's no difference between them. So in this particular case, talking about what is the major and the minor product is immaterial. It's always the same product. Well, let's go to let's just go one step further. Let's go to this molecule. And you can see I'm just doing lines for the hydrogens that are irrelevant. They're part of the molecule here, but they're not hydrogens that can leave with that OH group to form water. Only these two. In other words, you can't pull this hydrogen off with that OH group and be figuring out where's the double bond. The double bond is always going to be between the two carbons that contributed the hydrogen and the hydroxyl group. Okay? So, in one case, if we removed this, can you see we would get this? Yes? And if we moved this, I'll put a circle around this, what would we get? Where would the double bond be? All right there on the end. All right, so now we got a situation where there are two distinctly different possible products. And the question arises, do you get 50-50? Do you get more of one than the other? And just like Markovnikov, when he was hydrating alkenes and making alcohols, was faced with that decision or that situation, and he figured it out. How did he do it? With a lot of laboratory work. He did it. He did a lot of reactions, and then he said, well, what am I getting? What am I getting? What am I getting? Do I see a pattern here? What's the pattern? Zaitsev did the same thing. He took a bunch of alcohols and he dehydrated them. And he says, what am I getting? He looked at the products coming out. And he probably got a little bit of both. He got some of each of these, but one was a major product. And so by doing it over and over and over again, he came up with Zaitsev's rule. And we'll come back and look at those molecules and apply this rule to it. Right here, Zaitsev's rule. The product that gives the highest number of carbons attached to the double bond is the major product. Another way of saying this is the more substituted double bond. The more substituted with carbons. The more substituted double bond is the major product. The product that is more substituted. All right, let's go back here and see what I mean by substituted. So here's our two. So what we do here is we focus in on this double bond. And we say how many carbons are there attached to those two carbons. And we have 1, 2. So there are 2 carbons substituted on the double bond. Over here, we have 1 carbon. Now, we don't count how long is the chain behind it. What we're really asking ourselves is this. what is around this double bond? What is around it? Well, we got a hydrogen, we've got a hydrogen, we've got a hydrogen. That's what we've got here. And we have a carbon. So I don't even have to worry about this other carbon. That's what we have around it. So there is only one carbon substituted onto this. And so this over here is, with two carbons substituted, is our major product. Okay, so that's what you want to do. You want to look at the two carbons in the carbon-carbon double bond. You don't count them. They don't count. What you are counting is what is attached to those two carbons. There can be 4 things attached. How many of them are carbons? And so if you were asked for the major product, this would be the major product. It would be, so 2-butanol is going to form 2-butene. All right. Here you see Zaitsev's rule, the more substituted alkene. Zaitsev rules applies to determine the major product. And what are you going to be looking for? The more substituted alkene. So if you look at this right here, what does this look like? If I was given a test and was asked to do this, I probably would come down here and redraw this. Something like this. Redraw it something like this so that I could really kind of focus in right here. Say, okay, I can see. I can get a water molecule right here. I'd get a double bond right there. I can get a water molecule right here. I'd get a double bond right there. There's our products. This water molecule leaves, you get that top product. This water molecule leaves, you get that bottom product. So really, so on the top, you can see our double bond has 1, 2, 3 carbons on it. It has 3 carbons substituted on it. The bottom one, it probably would be better if we just focused right there. That double bond only has 1 carbon directly attached to it. Yes, there are 3 carbons on that substituent sitting out there, but these other ones don't factor in to the accounting here. We only account for that 1. So this is only singly substituted. And so it is the minor product. The upper one is the major product. Okay, do you see how to apply Zaitsev's rule? Let me give you one more really easy example, but it proves a point. You're not going to always have a major and minor product. So imagine I give you this alcohol. I'll draw it like this. So here we have 1 pentanol. So go ahead and figure out what would be the product of the dehydration of 1 pentanol. do you have a lot of choices here? Is there a major and a minor product? Is there a product? So what is the product? 1-pentene. All right, we're going to remove that right there. There is only one place. This is what really the correct answers to these kinds of questions are going to have the double bond in a particular place. It's not just that it produces an alkene, it produces a particular alkene. And you figure that out by knowing that water is H2O, and that OH needs a hydrogen, and it can only get it from an adjacent carbon. And so it ends up being between those two carbons that the double bond forms. This is singly substituted. I'm starting to draw the line in the wrong place. Yeah, there's 3 carbons going along there, but there's only 1 carbon. The other 3 things on this double bond are hydrogens. And so really, in general, primary alcohols are going to form alkenes with a double bond on the end. You're not going to be in this quandary over which product until you start looking at things like, where did our butene go? Oh, previous slide. Until you start looking at things like 2-butanol or 2-pentanol or 2-hexanol. When you have an OH group on a carbon and there's a hydrogen on either side of it, now you have the possibility of more than one product. Okay, so take a look at number 4 and take a few minutes right now. Finish number 4. All you need to do is draw the major product. Or do you have to name it also? Does it say name it?
It says name it.
Okay, so draw the major product and name it. On. Oh, there we go. I think I can make it through here. Let's carry on. There's a few more things to cover. In chapter 12, we need to cover ethers, phenol, which is an aromatic alcohol. So let's take a look at those. Thiols. You need to know what a thiol is. Well, here's one more example. Here is a cyclical alcohol, but it is substituted here. Without the methyl group there, that would be cyclohexanol. So we have 2-methyl cyclohexanol. This would be carbon number 1, carbon number 2. Just keep in mind that there is a hydrogen right there, and there is a hydrogen right there. Even though we got a cyclical alcohol right here, we do have carbons on either side of that OH, and there's a hydrogen, there's a methyl. So we could remove that water molecule and get a double bond right there, and we'd have 2 carbons on it, on that double bond. Or we could remove that hydrogen with this hydroxyl and get the double bond right there. And as this is pointing out, that would be the major product, because we would have a carbon substituted there, a carbon there, and we have a carbon there. We would have 3 carbons. I mean, just keep in mind, there's a carbon there, and there's a carbon there. So we would have 3 carbons attached to that double bond. So that would be the major product. If we got the double bond over here, we would only have this carbon and this carbon attached to it. So there's just one more example. All right. There is another way to dehydrate. In these other examples here, we are dehydrating. Where's the water coming from? The water is coming from a single molecule. Each molecule is delivering one H2O molecule in the dehydration. So that's dehydration. It's the elimination of water. But in ethers, and this slide is, we're going to get more slides on ethers, but let's go ahead and introduce it right here, because I'll probably forget to come back to it. Ethers are formed when we dehydrate between two alcohols. Let me show you what I mean. Let's take a simple alcohol that where you can't dehydrate methanol and form an alkene. Can't do that. Why? Because an alkene is a carbon-carbon double bond. By definition, it requires two carbons. It requires two carbons to have a double bond between two carbons. Methanol only has one carbon in it. That's not why you can form ethers with it, but I'm just using that as an example to show you I can't get an alkene here, but I can dehydrate. This is dehydration, or these two molecules are condensing on one another. They're going to eliminate this water, and what are we going to form? We're going to eliminate water, and over here we have a carbon and an oxygen. Look in here. If we remove that water molecule here, we still have that carbon and that oxygen, and we have that carbon. So where we had a hydroxyl on both molecules, we've now linked them together through a carbon-oxygen-carbon bond, which is an ether. This is the ether bond or ether linkage. That's an ether bond. That's the ether functionality. The very first day, chapter 10, where they listed all the functional groups, this would have been one of them. Carbon, oxygen, carbon is an ether. Okay, we'll come back to this in a minute. Here's a decent little summary of reactions. Let me tune this up a little bit. For the preparation of alcohols, at the top here, you might want to put the hydration of alkenes, forms alcohols. The hydrogenation of a carbon-oxygen double bond, this would be an aldehyde or a ketone, forms alcohols. Oxidation, we followed that. Here's the primary. You get an aldehyde or a carboxylic acid. It can go to carboxylic acid. Secondary, you get a ketone. And the tertiary, you get no reaction. And then what we've just covered is, first of all, you can dehydrate an alcohol to form an alkene. Zaitsev's rule applies here. Or you can dehydrate between two alcohols and form an ether. So there's a kind of a reaction summary for chapter 12. All right, a couple loose ends to kind of pick up. So, and some of it is vocabulary, just learning what things are called. Here is benzene with an OH group on it. That is phenol. Phenol. It's an aromatic alcohol. You should have a 3x5 card on that. So know the structure of phenol. By the time we get through chapter 15, I expect you to have a pretty neat little collection of 6-membered rings. Cyclohexane, cyclohexene, benzene, toluene. Now phenol, trying to think what else we looked at there. But we'll see some more as we move along. Just a benzene ring with something on it. You don't need to memorize these, but just to kind of show you the variety of things. Hexachlorophene is an antiseptic. Hexylresorcinol, antiseptic. And here, look at this. What does O stand for? Orthophenylphenol. That's a mouthful. Orthophenylphenol, antiseptic. Phenol, there's phenol right there. Phenol. But here's the major parent compound. So this is carbon 1. As you go around this ring here, this is the ortho, meta, para positions. So in the ortho position, the very next carbon, you have a phenyl substituent. So there's orthophenylphenol. Okay? Like I said, you don't need to memorize those, but I'm not going to worry about this reaction. Phenol is slightly acidic. Now that is unlike most other alcohols. Methanol, ethanol, propanol, isopropanol. You put those in water, they'll dissolve in water, but they're not acidic. Acidic means that hydrogen could hydrolyze off of there into the water and make the water acidic. That's not what happens when you put ethanol into water. It dissolves in the water, but the OH stays on the alcohol. All right, back to the ethers for a minute. Here's your ethers. Here's a model. We've got a carbon-oxygen-carbon bond. We've got a methyl on each side of this oxygen. So a very simple name for this would be dimethyl ether. Dimethyl ether. All I'm doing is just naming what's on either side of the oxygen. A little bit about the properties of ethers. And the favorite thing to look at is particularly when we compare molecules that have similar molecular weights. So what do I have here? Butane, molecular weight 58. I've got methoxyethane or methyl ethyl ether. Yeah, ethyl methyl ether. It's a simple name right there. And propyl alcohol. And if I remember what boiling points are kind of telling you. Are the molecules attracted to each other to any great extent? Butane, no. They're nonpolar. They don't have an affinity for one another. So they boil easily at around 0 degrees centigrade. They're boiling. They've turned into a gas, butane. Propanol has a strong attraction. So if I get these 3 carbons here, I got another propanol over here. And what do I get? I get these hydrogen bonds between propanol molecules. And so they don't really act like they're 60 molecular weight. They act more like they're almost 120. They're kind of stuck on the molecules in the liquid phase. And you don't get them to boil until you break that attraction, hydrogen bonds. Well, what about this one? So 0, let's say 100, 10. So around 10 degrees centigrade enters our ether. Yes, a little bit higher than this, but significantly lower than that. Why? There's no hydrogen on that oxygen. There's no hydrogen there to form a real polar oxygen-hydrogen bond. So they're slightly more polar than alkanes, but not a lot. A little bit more polar than alkanes, but nowhere near as polar as alcohols. Naming them, well, we'll look at a couple. Don't expect a whole bunch of things. Just how to handle simple ethers. All right? In simple ethers, you would just say, okay, I got a carbon, oxygen, carbon here. This is an ether. What is on each side of this thing? The parent name is going to be ether. It's an ether. What are the two things on each side of the oxygen? Carbon, but what are those carbon groups? What are those? What would you call those at a substituent level? Josiah? Methyl. We got a methyl. What else do we have? What's this one? Isopropyl. That's an isopropyl. So we could call this isopropyl. Matter of fact, I think the names are here. What about this one? So this is isopropyl methyl ether. What about this one? What is this? Ethyl. And what is this? It's benzene, but what do we call benzene when it's hanging on a carbon or hanging on a molecule? Phenyl. So ethyl. So here we've got isopropyl methyl ether, and here we have ethyl phenyl ether. We're just naming the two things on each side of it. That will work sometimes, all right? But not always, all right? So that works with simple. Simple means you got a methyl, an ethyl, an isopropyl, a propyl, a phenyl. Okay, we can handle that. But how do we handle this? Okay? 1, 2, 3, 4, 5. You say, well, why can't we call that methyl pentyl? Well, we could. But what would you call... Then what would you call this? Okay? Just look at this. So on this side of the oxygen, we got 5 carbons. On this side of the oxygen, we got 5 carbons. I could draw this a bunch of different ways. I could have boom, 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 and then 0, and have 2 more carbons coming down here, so you have 5 carbons. You can have a bunch of different situations where there's 5 carbons on one side and 1 carbon on the other side. So what do we do here? Well, we treat this as if this OCH3 group, as if it were a substituent. So that is called a methoxy. Just like you already know that that is called a methyl. See, we're taking the methyl and we're inserting an oxygen in there. It's a methoxy substituent. It's not a methoxyl, it's a methoxy substituent. And so then you can see what we're doing now is we're not just using a simple name, we're using an IUPAC naming, which says, okay, find the longest chain, 1, 2, 3, 4, 5. The methoxy is on the first carbon, so it's 1-methoxypentane. And look, if you looked at it right here, here's carbon number 1, 2, 3, 4, 5. So this would be 2-methoxypentane. We can now handle a 5-carbon chain with an ether coming off the side of it. And we just have to figure out where is that ether, what carbon. What carbon is it attached to the chain? You with me? So 1-methoxypentane, you draw that and you say, well, what kind of molecule is that? It's an ether. I got a carbon-oxygen-carbon bond there. And in general, we would call it an alkoxy substituent. Happens to have 1 carbon, it's methoxy. So you could have an ethoxy, propoxy substituents. But we probably won't go beyond a methoxy. You can burn ethers. Don't worry too much about that. That would be a little bit more complicated to balance. You've got oxygen here too. So you've got oxygen in everything. Your starting materials and your both products. Both reactants and both products contain oxygen. You just have to take that into consideration when you balance it. I don't worry too much about that, but I just want you to know you can burn them. Here is they're making a symmetrical ether here. What do they mean? Both sides of the oxygen have the same thing. Symmetrical. So you have here you would have diethyl. Ethyl and ethyl, diethyl ether. Medical uses of ethers, back in, I don't know when, 40s and 50s, they were starting to use ether when you went to the dentist, and other times, but, dentists in particular, we're going to, we got to drill this cavity, we're going to use some ether, put you to sleep for a period of time. But there are many derivatives of this that are used as anesthetics. So here's penthrane. So we got a methyl and an ethyl, but this ethyl has 4 halogens on it. Penthrane. I talked with a master's level nurse anesthetist, the military, I think it was an Army. I was on a flight and just talking to the guy, and I asked him about what anesthetics do you use, and he started making a long list of different compounds like that and others. And he said, what are we looking for? Well, vapor pressure. But what is the boiling point of that? Solubility in the bloodstream. How soluble is it? Because it's basically, as they administer it, it's dissolving in the bloodstream. It's affecting the nervous system. The body is exhaling it. And the rate at which it exhales it has to do with the vapor pressure and the solubility in the bloodstream. So the more soluble, the less it evaporates when it comes through the lungs. And other things. He said we have to be aware of pH and density, and said in some cases density. If a person is on their back and we want to numb the spine. and we want the anesthetic to kind of pull down into the spine area. We use a dense anesthetic. He was just going through all this stuff. So it was pretty complicated. But all this stuff was chemistry. It was a lot of chemistry. He said the doctor will say, oh, I want this patient to be alert in 30 minutes. So we look at our possible anesthetics. What will the patient exhale in 30 minutes? What will be released from the body in 30 minutes? If the doctor says we want this patient to be pretty out of it for 4 to 6 hours, then they look at a different anesthetic. And then, of course, we know that dose is very important. All right, so that's anesthetics, and a lot of them are ethers. I don't know that they all are, but many of them are. Okay, just for terminology's sake, I want you to understand what a thiol is. You know what an alcohol is. You have a hydroxyl group on a carbon. That's an alcohol. Thiols, you have an SH group on a carbon. And that would be a thiol functional organic molecule. So here's 3-methyl-2-butane thiol. So we have butane thiol. It's not butanol, it's butane thiol. Water is H2O. Sulfur combines with hydrogen in H2S. Keep in mind where the S is. It's right underneath the oxygen. So from 1305, what you learned is that elements that are in the same family have some similarities. And here's a similarity. Oxygen combines with 2 hydrogens to form water. Sulfur combines with 2 hydrogens to form hydrogen sulfide. Now that's probably where the similarities end, because thiols are have extremely offensive odors. These are the kind of compounds that skunks produce. They produce thiols. And what do we mean by extremely offensive? Well, your nose will detect a thiol in the parts per billion level. Not parts per 100 or 1,000 or million, billion. So extremely low concentrations of thiols, you pick it up right away. Whoa. And you know that just from driving by a skunk on the road, that you can smell it. You don't even have to run over it. You just drive by it. Okay, so here's Pepe Le Pew on Valentine's Day taking his girlfriend a set of roses. The roses smell good. All right, the roses are smelling good, but nobody wants them. Pepe doesn't know that he doesn't smell good. Here's what he produces, these thiols. Trans-2-butene-1-thiol, 2-methyl-1-butane thiol. There, you see the thiol up there. There's the thiol right there, attached to these molecules. Thiols will kind of overwhelm you. I mean, you're offended by their odor, but with time, 20, 30, 40 minutes, if the concentration is too high, your olfactory glands will kind of shut down and just say, They will lose their sensitivity to it. I was doing research over 20 years ago. We were working with platinum compounds, and you can bind platinum onto things through sulfur substituents on like a column. And so I ordered some thiols, and they were coming by UPS. I shouldn't laugh. I was at work. I got a call. Riak, did you order some chemicals? The UPS doc has just called. 3 of their men went home sick. You know, the bottle broke. So this bottle of thiols broke, and our DPS kind of people, our security people, drove out to there and put this in the back trunk of the car and drove it back out here, and I had to go get it and do something with it. But it caused quite a stir. Just a little bottle. I mean, I ordered a tiny little bottle of thiol, and it broke in transit and caused a lot of problems. So yeah, these are very offensive. So I kind of remember these things. Don't worry about too much naming. Okay, there's ethane thiol, 1,2-ethane dithiol. Don't worry about too many. But if you is a multiple choice, the following is which of the following is a thiol functionality? You should be able to pick that out. What are we talking about? We're talking about a sulfur functional organic molecule. And then in the biochemistry arena, and don't worry too much about this, you'll be drawing this in chapter 18. This is cysteine. It's an amino acid. It is an SH, it's got an SH functional group on it. It's a required component of our protein. And it will form a disulfide. So these two SHs on two cysteines will form a disulfide, what we call a disulfide bridge, or a sulfur-sulfur bond. And that ends up playing some critical roles in protein structure. But this is chapter 18, when we get to proteins, amino acids and proteins. And that will be chapter 18, insulin. Okay, another reaction summary. Just like the other one, is very much like the other one. What we're doing here is water plus an alkene, and we're going in this direction. And over here, we're hydrogenating, going in this direction. I'm not going to dwell on that one. That one's very much like the earlier slide I showed you. There's a summary of reactions, and there is a summary of reactions, like those other slides, but this is being a little bit more explicit. An alkene plus water forms an alcohol. So here, first category is how do you make an alcohol? You could react an alkene plus water to form an alcohol. You could take an aldehyde or a ketone and hydrogenate. This is hydrogenation. Form an alcohol. Oxidation, we talked about on Wednesday. Primary to an aldehyde, secondary to a ketone, tertiary, no reaction. And then here are the two dehydration reactions at the bottom. Intramolecularly, within one molecule, you get an alkene. You're splitting out water. Intermolecularly, between two molecules, again, you're splitting out water, and you're forming an ether. So there's your summary.
So we don't need to worry about diols?
Diols. What do you mean? Worry about them in what sense? Naming them?
I thought that was in the chapter. So
There can be diols, like ethylene diol, not reacting them, but this is ethylene glycol, or 1,2-ethane diol. That's 1, 2. This is antifreeze. That's about all you need to know about diols.
okay.
That if there was a molecule with two OHs on it, it would be a diol. There is a molecule in chapter 17 later that is a triol. This is glycerol, and it's a triol. That would be 1, 2, 3 propane triol. So just know that just like there is a dimethyl or a diene, there can be a diol.
I was getting confused between triol and diol.
No, yeah. This is a triol, and then this is a thiol. Yeah, that could be a little confusing. let's see. This is a chapter 12 summary. Chapter 11 summary, let me put right underneath it. Chapter 11 reaction summary. Most critical thing is 4 addition reactions to alkenes. Hydrogenation. Halogenation. Hydration. Hydrohalogenation. They have a name. They all start with an H. Okay, know the names of those reactions. And what are you doing when you name those reactions? You are naming the reactant. This is what is reacting with the double bond. This is what is adding across the double bond. 2 hydrogens, 2 halogens, an OH and a hydrogen and a halogen. So they all have names. I won't write them all down here, but just for example, I'm sorry, writing the wrong name. Hydrogenation, which is what they do to vegetable oils. Hydrogenation, halogenation, hydration, hydrohalogenation. You should be aware of, you don't need to kind of write out a bunch of reactions, but know that you can take a double bond and polymerize it. And ethylene becomes polyethylene. Well, there's one other reaction. There is the, what is the other reaction? Oh, okay, the other reaction is benzene plus a halogen, the halogenation of benzene. And remember, what you're going to get here is you're going to get 1X and HX. So if you react chlorine with benzene, you're going to get chlorobenzene and HCl. And this is catalyzed by iron chloride. Am I missing a reaction for chapter 11? Is that it? Seems to be it. This is key. And then chapter 11, or chapter 10. Is you have combustion. Remember, chapter 10 is alkanes. You have combustion and you have halogenation. And complete combustion is an alkane plus what? Oxygen yields what? And, all right, that's complete combustion. Incomplete combustion is very, very similar, except you're producing primarily carbon monoxide instead of carbon dioxide. But this is what we are usually trying to do when we're burning an alkane, is completely burn it. This is the complete combustion of it. You get the most energy when you completely burn it. And you get a gas that, although we can't survive in a carbon dioxide environment, it's not poisonous. It's just keeping away oxygen. But we can't survive in an atmosphere that contains carbon monoxide. Even small amounts of it would over time wear you out. because your body is soaking it up like a sponge. It's soaking the carbon monoxide up. Okay, any questions? Got 5 minutes for any broad questions.
Primarily multiple choice, or?
Yeah, I think the test is multiple choice, and I believe it's 35 to 40. You'll probably have plenty of time. I mean, get here at 12:30, so you have plenty of time. But I don't think you'll be stressed time-wise.
Is the chapter 10 quiz pretty representative of the types of?
Yeah, except like for multiple choice, it might say which is the correct structure of this molecule, or it'll have a bunch of it'll have a molecule and it'll say what is the correct name of this molecule, or what is the correct condensed formula for this molecule.
You want the homework?
Yeah. Would you pass the homework up to the front, please? Oh, I'll try to get these graded. When am I going to do that? I will try to get them graded. But they'll probably be available like Wednesday morning. Wednesday morning. LOH 306. You can pick up. Pick it up. Yeah. No, I will be blank sheet.